Pick up a gold wedding ring, about 6 grams of metal tau. It looks simple, a loop of warm yellow metal. Here's what's actually in your hand: the remains of a collision between two dead stars. An event that happened before our solar system existed. An explosion so powerful it was brighter than 1 billion suns and rippled through the fabric of space-time itself. Every atom of gold on Earth, every ring, every bar, every fleck in every river was forged in an event like that. And until very recently, we had no idea. Gold has always been strange. It's one of the few metals that doesn't react with oxygen. Iron rusts, silver tarnishes, copper turns green. Gold just sits there. You can bury it for 3,000 years, dig it up, and it looks exactly the same. Every civilization that found gold treated it as something almost supernatural. And there's a physics reason for that. Gold has 79 protons, making it so heavy that its innermost electrons orbit at over half the speed of light. At those speeds, Einstein's relativity kicks in. The electrons gain mass, their orbitals contract, and that's what makes gold chemically inert. Gold is, in a very literal sense, a relativistic metal. But here's the deeper question. Where do you get an atom with 79 protons? Stars are the forges of the universe. They fuse hydrogen into helium, helium into carbon, all the way up the periodic table. But they stop at iron. Element 26. Every star that has ever burned has hit that same ceiling. Iron is element 26. Gold is element 79. That's a gap of 53 protons. And no ordinary process in the cosmos can cross it. So how did gold get here? To answer that, you need to understand what a star actually does. A star is a thermonuclear reactor held together by gravity. Hydrogen atoms in the core fuse into helium at 15 million degrees, converting mass into energy, about 4 million tons every second. That energy is what makes stars shine. Our sun has been doing this for 4.6 billion years, but bigger stars burn faster. A star 10 times the sun's mass gets through its hydrogen in just 20 million years. And when the hydrogen runs out, the star doesn't die, it evolves. The core contracts, heats up, and starts fusing helium into carbon. Then carbon into neon, neon into oxygen, oxygen into silicon. Each stage burns hotter and faster. Hydrogen lasts millions of years. Silicon, the very last fuel, burns for about 1 day. And then it produces iron. Using anything lighter than iron releases energy. That's what powers stars. But fusing anything heavier than iron absorbs energy. The star would need to put energy in rather than getting energy out. So, the moment a massive star builds an iron core about 1.4 solar masses, the fusion engine shuts off. Gravity wins instantly. The core collapses at 1/4 of the speed of light. The outer layers crash down, bounce off the core, and blow the star apart in a supernova, releasing more energy in 10 seconds than our sun will produce in its entire lifetime. But even a supernova can't make gold. The conditions are extreme, but they're the wrong kind of extreme. There aren't enough free neutrons and they're not concentrated enough. The periodic table, as far as stars and supernovae are concerned, effectively stops around zinc, element 30, gold is element 79, platinum is 78, uranium is 92. To reach those, you need a completely different kind of event. The mechanism that builds gold is called the R process, rapid neutron capture. Here's the idea: protons are positively charged, so adding them to a nucleus means fighting electromagnetic repulsion. That's why stellar fusion stalls at iron. But neutrons have no charge. They slip right in. If you flood a nucleus with thousands of neutrons in a fraction of a second, it absorbs them faster than it can decay. It becomes bloated, unstable, grotesquely neutron-rich. Isotopes that exist for milliseconds. And when the neutron flood stops, those overloaded nuclei cascade through chains of beta decay, neutrons converting to protons, each step moving the atom up the periodic table until they land on stable elements: gold, platinum, uranium. The R process is essentially a shortcut. Instead of fighting repulsion to add protons one at a time, you sneak in through the neutron door, overload the nucleus, and let nature sort it out. 20 neutrons per cubic centimeter, temperatures above 10 billion degrees. And everything has to happen within about 10 seconds. For decades, physicists thought supernovae were the answer. But computer simulations kept falling short. The neutron densities were too low by orders of magnitude. So theorists turned to something even more extreme: the collision of two neutron stars. A neutron star is what's left after a supernova. About 1.4 solar masses crushed into a sphere 20 kilometers across. A teaspoon of it weighs 1 billion tons. It is essentially a giant atomic nucleus the size of Manhattan. Now imagine two of them spiraling toward each other over millions of years, accelerating until they're orbiting hundreds of times per second at 2/3 the speed of light. And then they collide. The debris sprays outward at 20 to 30% the speed of light, carrying exactly the neutron density, temperature, and timescale the R process needs. The theory was elegant. The math worked. But for decades, there was no proof. Until 2017, at 8:41 a.m. Eastern Time on August 17, 2017, a gravitational wave passed through Earth. LIGO detected it at both facilities, Hanford, Washington, and Livingston, Louisiana, simultaneously. A third detector, Virgo in Italy, confirmed it. The signal lasted about 100 seconds, sweeping upward in pitch like a cosmic chirp, the unmistakable signature of two massive objects spiraling into each other. The waveform matched two neutron stars merging 130 million light-years away in a galaxy called NGC 4993. Then, exactly 1.7 seconds after the signal peaked, NASA's Fermi satellite detected a short gamma ray burst from the same direction. That was the collision itself. This had never happened before. Gravitational waves and light from the same event. The alert went out immediately. Within 11 hours, telescopes in Chile spotted a new point of light in NGC 4993 that hadn't existed before. Then Hubble turned to look. Then Chandra. Then Spitzer. Over 70 observatories across every continent and in space pointed at this one galaxy. It became the most observed astronomical event in human history. What they saw was a kilonova, an explosion roughly 1,000 times brighter than a nova, powered by the radioactive decay of freshly created heavy elements. In the first days, the kilonova glowed blue, lighter R process elements radiating as the debris cooled. Then the color shifted to red as heavier elements like gold and platinum dominated. The spectra confirmed everything the theorists had predicted: strontium, platinum, gold. The estimates from this single merger, about 10 Earth masses of gold, along with platinum, uranium, thorium, and dozens of other elements heavier than iron, all produced in less than a minute, all flung into space at 1/4 the speed of light. For the first time, humanity watched the universe forge gold, 130 million light-years away. So here's the actual history of the gold in a wedding ring. About 4.6 billion years ago, there was a cloud of gas and dust in this arm of the Milky Way. Mostly hydrogen and helium from the Big Bang, mixed with carbon from dying red giants and oxygen from ancient supernovae. And woven through it, in tiny traces, were atoms of gold, platinum, and uranium, sprayed there by at least one neutron star collision that had occurred nearby millions of years before. That cloud collapsed. The center ignited and became the sun. The remaining material formed the planets. Earth came together as a ball of molten rock and metal, and because gold is a siderophile, an iron-loving element, nearly all of it sank to the core. The Earth's core holds an estimated 1.6 quadrillion tons of gold, enough to coat the planet half a meter deep, but it sits 2,900 kilometers below our feet. We will never touch it. So, why is there any gold near the surface? Between 4.1 and 3.8 billion years ago, a swarm of asteroids hammered the inner solar system, the Late Heavy Bombardment. Those impactors carried gold and delivered it directly into Earth's crust after the core had already sealed itself off. Over billions of years, geological processes, volcanoes, tectonic movement, hydrothermal circulation, concentrated that gold into the veins and deposits we mine today. The concentration in Earth's crust is about 0.004 parts per million, 4 gold atoms for every billion atoms of rock. All the gold ever mined in human history, every Egyptian death mask, every Roman coin, every bar in Fort Knox, every ring on every finger, totals about 212,000 metric tons. A cube, roughly 22 meters on each side. You could fit it all under the Eiffel Tower. Every single atom was forged in the collision of dead stars before our planet existed. And for all of recorded history, every civilization that worshipped gold, nobody knew where it came from. We built economies on it, fought wars over it, toppled empires for it. And the answer was hiding 130 million light-years away, detectable only by an instrument we invented in 2015. The universe made the first 26 elements easily, inside every star. The rest required catastrophe.